Hey guys, today we're going to be talking about trig substitutions to solve integrals. Now this is an advanced BC topic, but first of all you're going to have to know some basic stuff, and this is the one time that I'm going to say that pre-calc prepares you for calc, and that is with basic trig. So you must be very familiar with these Pythagorean identities to be able to do trig substitutions at all. So the first one is the very simple one that everybody learns. So everybody who might need this video, you should probably already know this, but cosine theta squared plus sine theta squared equals 1. That's basically just Pythagorean theorem. So here's a little visual if you need it. Alright, now given this identity, we can divide every term by cosine theta squared to get a new identity. So cosine theta squared over cosine theta squared, that's 1. Sine theta squared over cosine theta squared, sine theta over cosine theta is tangent, so that's 1 plus tangent theta squared. And 1 over cosine squared is secant squared. Alright, so these two identities are the key to doing these so-called reverse trig substitution integrals. Now, why do we need these identities? Well, you can see sine and cosine relate to each other with the first identity. Tangent and secant relate to each other with the second identity. And let's take a look. Let's take a look at the more calculus-y part now. So the derivative of sine theta, that is just cosine theta. So, and the derivative of cosine theta is just negative sine theta. And finally, the derivative of tangent is just secant squared of theta. So if you don't know any of this, you should probably go review some of your pre-calc stuff before you jump into this calc BC stuff. So noticing how we have the basic trigonometric functions, they're related, their derivatives are related to each other, so let's see how it works. Let's say we're trying to evaluate the integral of 1 over the square root of 1 minus x squared dx. Okay, so it doesn't look like there's really another way to do it, but what we notice is that we have a 1 minus x squared down here. And what does that remind you of? So let's try something. Let's try the substitution x equals sine theta. And dx equals cosine theta d theta. Remember, we have to substitute both the variable and the differential. So the dx becomes cosine of theta d theta. And the denominator becomes 1 minus sine theta squared. Now, what is 1 minus sine theta squared? Well, by that identity from previously, it's just cosine squared theta. So now the 2 and the square root cancel out. So you might think if we're taking the square root, we're going to need to put an absolute value here. But since inside the square root, it always has to be positive, otherwise you can't take the square root and end up with a real number. It's always positive, so the absolute value sign doesn't even matter. So now our integral is actually a lot easier because the cosine theta on the numerator cancels out with the cosine theta on the denominator. So we just integrate d theta, or 1 d theta. And that is just theta plus c, obviously. Now we have to put it back in terms of our original variable. So we solve for theta. We get theta equals arcsine x. So our integral is equal to arcsine x plus c. All right. Now let's go to another example. Let's do, it looks very similar. 1 over 1 plus x squared d theta. Not d theta, dx. Okay, so now it looks, we have to try to substitute something again for it to try. You know what? Just to make it fun, let's make a definite integral this time, from 0 to infinity. So now if you substitute x equals sine theta or something, it won't work because 1 plus sine theta squared or 1 plus cosine theta squared doesn't even is not equal to anything. And another hint you might want to take is that the denominator is always positive, so x can actually be any real number. So you want to think of a trigonometric function with a range that is all real numbers. And guess what? We have one right here. Very good for us. X equals tangent theta. So now we also do have to do dx. Dx equals secant squared theta. But remember, we also have to change the bounds. So at x equals 0, we have 0 equals tangent theta, so theta equals 0. And when tangent theta equals infinity, theta equals pi over 2. So our integral becomes from 0 to pi over 2 of, again, we must replace the differential also, secant squared theta d theta, and on the bottom we have 1 plus tangent theta squared. However, 1 plus tangent theta squared is, from our Pythagorean identities, secant theta squared. And everything cancels out again, so we just have the integral from 0 to pi over 2, again 1 d theta, and that's just equal to, let's evaluate theta at 0 and pi over 2, and computing the definite integral, we just have pi over 2. So basically, in both of our examples here, we see a quadratic on the denominator in some form, and so when you want to use sine or cosine is if it's something like a constant minus a quadratic term, like 1 minus x squared, especially when it's square rooted. So the power on from the differential in the numerator can cancel out with the denominator. Now, if it's 1 plus x squared or anything that even remotely resembles 1 plus x squared, it's a quadratic term plus a constant, then you want to think about using something like tangent theta, because tangent theta has a range of all real numbers, while sine theta and cosine theta are constrained between -1 and 1, and that's why it fits the square root so nicely. Now, you could probably stop the video here, but I want to work through a bonus example. Like this, you'll probably not see an example as complicated as this on the BC exam, but I just want to show you the power of how far the trig substitutions can actually extend. So let's do 1 over x squared plus x plus 1 dx, the integral thereof. Now, this is we can't factor this quadratic on the denominator at all. In fact, it doesn't even have any real roots, but what we can do is we can try to complete the square. 1 over x plus 1/2 squared, and then plus 3/4. So now it looks like something squared plus a constant on the denominator. So let's do a substitution, a trig substitution. But it might seem a little more complicated than usual. So let's let x equals √3 over 2 tangent theta minus 1/2. Now that looks very cumbersome, but it actually works out really nicely because dx is just simply √3 over 2 secant squared, and the constant 1/2 doesn't matter. So let's see what we have here. On the top we have √3 over 2 secant theta squared. On the bottom, so x plus 1/2, that's just √3 over 2 tangent theta squared. And the whole thing squared, so we have to square both things. So the √3 over 2 squared becomes 3/4. And the tangent theta squared just stays tangent theta squared plus 3/4. And in fact, let's factor out a 3/4 from everything. So we have tangent squared plus 1. Okay, now doesn't that look familiar? That's just secant squared. So it all cancels out pretty nicely again. So we're only left with the integral of 2√3 over 3 d theta, which is just 2√3 over 3 theta plus c. Now all we have to do is solve again for theta. So we do x plus 1/2 equals √3 over 2 tangent theta, and then isolate tangent theta, take the arctangent. You're left with theta equals 2√3 over 3. Forget that. The inverse tangent of 2√3 over 3 times the quantity x plus 1/2. So our entire integral is 2√3 over 3 times the inverse tangent of 2√3 over 3 all times x plus 1/2 plus c. Okay, so this was a very tedious example to work through, but now you can see the power of the trig substitutions. Basically anything that looks like a quadratic plus a constant term, even if it requires completing the square, that's where you could use the tangent substitution. And again, for same thing here. If you have to complete the square within a square root to get something that looks like a constant minus a quadratic term, there you could use a sine or a cosine. It actually doesn't matter. So hopefully that made sense to all of you BC people, and congratulations for taking such a hard class, and I hope this helps. See you later.